Picture this. You are strapped inside a metal cylinder, the size of a city bus. There are no windows. Outside, there is nothing, just black, just silence, just 140 million miles of empty space between you and every single person you have ever loved. You have been traveling for 6 months. You are not even halfway done. And the most terrifying part, the thing nobody talks about, is not the radiation. It is not the isolation. It is not even the landing. It is something that could kill the entire mission before it ever begins. Something that no rocket engine, no amount of fuel, and no amount of bravery can fix on its own. I will tell you exactly what that is at the very end of this video, and I promise you it will completely change how you think about going to Mars. But first, quick question. Where are you watching this right now? Are you on your phone, on a laptop, maybe on a TV? Drop it in the comments. I am genuinely curious. Now, let me take you back to the beginning. Mars is 140 million miles away on average. That number sounds abstract until you realize it takes light itself nearly 13 minutes to travel that distance. A radio signal from Earth takes between 4 and 24 minutes to arrive at Mars, depending on where both planets are in their orbits. That is not a communication delay, that is a communication blackout. But before you can even think about the communication problem, you have to solve the first problem, and that problem is timing. Mars and Earth do not sit still. They are both orbiting the Sun, but at different speeds and at different distances. Every 26 months, they swing close enough to each other that the trip becomes practical. Miss that window, and you wait 2 more years. There is no shortcut. During the right window, the journey takes roughly 6 to 7 months one way. 6 to 7 months in deep space, beyond the protective magnetic field that surrounds Earth and shields us from radiation every single day without us ever noticing. Once you leave that bubble, the rules change. But here's the thing most people don't fully appreciate. The journey to Mars is actually 3 missions stitched together into one. The first mission is the trip there, 6 to 7 months. The second mission is the surface stay, and here's where it gets brutal. You cannot land on Mars and immediately turn around and come home. The planets have to align again. That takes another 500 to 600 days, more than a year and a half. The third mission is the trip back, another 6 to 7 months. Add it all up, you're looking at roughly 900 days away from Earth. 2.5 years. That's the minimum. That's if everything goes perfectly. Now ask yourself, what does it actually take to make that happen? Let us start at the bottom, literally, the ground. To go to Mars, you need a rocket powerful enough to lift everything off the surface of Earth. The crew, the food, the water, the medical supplies, the habitat, the equipment, the return vehicle, and all the fuel to power every single stage of the mission. The problem is physics. For every kilogram of cargo you want to send to Mars, you need several kilograms of fuel to launch it. But that fuel is also mass, which means you need more fuel to lift the fuel. The numbers compound on themselves until they become almost impossible to manage. Current estimates suggest a human Mars mission needs to land somewhere between 50 and 100 metric tons of cargo on the Martian surface. That is more than any rocket ever built has ever delivered anywhere. This is where Starship comes in. SpaceX has been developing a fully reusable launch system standing over 120 meters tall. It is powered by 33 engines on the booster stage alone. It is designed to lift 100 to 150 metric tons to low Earth orbit. But here's the catch. Even Starship cannot carry enough fuel to go from Earth orbit all the way to Mars, slow down, land, and then send a return vehicle back home. Not while also carrying a crew and everything they need to survive. So, the solution is orbital refueling. You launch the crew vehicle into orbit mostly empty. Then you launch a series of tanker spacecraft, one after another, each one docking and transferring fuel. somewhere between 8 and 16 tanker flights just to fill a single Starship before it leaves for Mars. This has never been done before, not at this scale, not by anyone. It is the first link in a very long chain of problems that all have to be solved in sequence. The second link is radiation. Outside Earth's magnetic field, the crew is exposed to galactic cosmic rays. These are high-energy particles traveling at nearly the speed of light. They pass through metal, they pass through flesh, they can damage DNA and cause cancer. They can damage the brain itself. Studies show that high-energy particle exposure causes neurons to lose complexity. Memory degrades, decision-making slows. Some researchers estimate that 1 in 5 crew members on a Mars mission could experience measurable cognitive decline just from the radiation alone. On top of that, solar flares can release bursts of radiation intense enough to be lethal within hours if the crew is not protected. Traditional shielding, like lead or aluminum, actually makes things worse by creating secondary radiation. So, engineers are developing lightweight materials with high hydrogen content, things like water barriers, polyethylene, and experimental nanomaterials that absorb radiation without scattering it back. The third link is landing. Mars has an atmosphere, but it's thin, less than 1% the density of Earth's. Thick enough to heat a spacecraft to extreme temperatures during entry, but not nearly thick enough to slow it down for landing. Anything we have ever landed on Mars before has weighed about 1 metric ton. Starship weighs 100 metric tons when empty. It is 100 times heavier than anything we have ever put on that surface. Parachutes will not stop it. Airbags will not stop it. The only way to land something that heavy on Mars is to fire rocket engines while traveling at supersonic speeds. It's called supersonic retropulsion, and until just a few years ago, engineers genuinely weren't sure it would work. Firing engines backwards through a supersonic shockwave seemed like it would tear the vehicle apart. But SpaceX's tests with reusable rocket boosters proved something surprising. The shockwave actually forms a protective bubble around the vehicle, stabilizing it during descent. The physics cooperate when you do it right. The fourth link is propellant production. The crew needs a rocket on Mars ready to launch before they ever arrive. But bringing all that fuel from Earth is not possible. The mass requirements are astronomical. So the fuel has to be made on Mars from Martian resources. The Martian atmosphere is mostly carbon dioxide. By reacting that CO2 with hydrogen, you can produce methane and water. Split the water to get oxygen and more hydrogen. Store the methane and oxygen as rocket propellant. A small version of this technology was tested on Mars in 2021 aboard the Perseverance rover. It worked. Oxygen was successfully produced from the Martian atmosphere. But a full-scale system needs to produce roughly 25 tons of oxygen over a year and a half. That requires massive amounts of reliable power, either from large solar arrays or compact nuclear reactors. Every single one of these links in the chain has to hold. If any one of them fails, the mission fails. If the refueling doesn't work, the crew never leaves Earth orbit. If the radiation shielding is inadequate, the crew arrives impaired. If the landing fails, none of the rest matters. If the propellant production fails, the crew can't come home. This is what it actually takes. And I haven't even told you the hardest part yet. Remember what I said at the beginning? The thing that could kill the mission before it ever starts? It is not a rocket failure. It is not a radiation storm. It is not even a bad landing. It is the people. A Mars mission puts human psychology under pressure that no training simulation can fully replicate. 6 people, confined in a spacecraft roughly the size of a large apartment, for 6 months on the way there, another year and a half on the surface, 6 months back. No escape, no privacy, no way to walk out of the room and cool down. When a conflict develops on the International Space Station, astronauts can retreat to different modules. They know resupply missions are coming. They know Earth is close. They know that if a real emergency happens, they can evacuate. On a Mars mission, none of that is true. Communication delays mean a crew member in a mental health crisis cannot have a real conversation with a therapist back home. They send a message, they wait 20 minutes, they receive a reply. That is not support, that is an echo. Studies of long-duration isolation show that interpersonal tensions escalate, sleep deteriorates, and small frustrations compound into serious fractures. And the research on radiation-induced cognitive decline adds another layer. Memory, attention, and emotional regulation all degrade under the particle bombardment the crew will face. NASA is developing AI-based mental health tools, cognitive self-monitoring systems, and crew selection processes designed to find people who are not just physically capable, but psychologically resilient, genuinely compatible, and capable of working through conflict in total isolation. But here's the honest truth. We do not fully know if it is possible to send 6 people on a 900-day mission to another planet and have all of them come back mentally intact. We have never done it. We have approximations, studies, simulations, but we have never done it. And that's the real frontier. Not the rocket, not the fuel, not even the landing. The real frontier is the human mind under conditions no human has ever faced. So, when will this actually happen? The first uncrewed Starship missions to Mars could launch as early as 2026 during the next favorable launch window. Cargo missions could follow in 2028, and a crewed mission, if everything works, perhaps 2030 or 2031. Most experts believe those timelines will slip. Building, testing, and certifying every piece of this chain takes time, and the consequences of getting it wrong are irreversible. But even if it takes until 2035 or 2040, we're still talking about within your lifetime, humans walking on Mars. Not a simulation, not a movie, the real thing. Here's what we know for certain. Every piece of this puzzle is either solved or solvable. The orbital mechanics are understood. The rocket is flying. The propellant production concept has been tested in the field. The shielding materials are improving. The landing technique works. What we do not know is whether we can assemble all of these solutions into one integrated system that functions reliably for 900 days with no margin for catastrophic failure and no rescue option. That's the challenge. That's the mission. That's why the people who go will be the most prepared, most tested, most psychologically resilient humans who have ever lived. And if they succeed, the first footprints on Mars will not just be a human achievement. They'll be proof that when a species decides to do something, truly commits to it across decades and billions of dollars and thousands of engineers and scientists, there's no distance too far, no problem too hard, no planet too cold, too distant, or too hostile. Mars is not a fantasy. It never was. It's a destination. And the clock is already counting down.